Cycle 2, Lesson 6, Solving Linear Quadratic Systems. You may recall from grade 10 that a linear system is two linear functions crossing. They usually will cross each other unless they have the same slope. They cross each other, and the solution to the system is the point of intersection. In other words, we're trying to find that point that satisfies both equations. It'll be, if they're linear, they're going to cross in one point. There's going to be an x and y coordinate, and they're going to, that's the only point that's on both lines. That's what makes it the solution. And there are three ways of doing it. The easiest way to see it is from graphing, because if you have the graph, then you just quickly look and see, okay, yes, that xy point ordered pair is the point of intersection. But we could also do it using substitution algebraically or elimination, also an algebraic method. Linear quadratic systems are solved much the same way, except that instead of having a single point for the solution, we could have up to two solutions, and we could have as few as no solutions. When we do it algebraically, we're going to see that substitution is pretty much going to be our go-to method. Elimination doesn't work so well for when we're doing linear quadratic combo. So, as I mentioned a moment ago, there can be really three different possibilities as far as the number of solutions goes. So if you have a parabola, like you can see here on the left, with a line that crosses through it in two different places, well, both of these points of intersection, this and this, both those points are on both the line and on the quadratic, and therefore they're both solutions to this system. The one in the middle, where it only touches in one place, is going to only have one solution. And you can see the one on the right, they never cross. And if they don't cross, there's no way that there can be a solution, because again, the solution is the point or points that are on both the curve and on the line. So there'd be no solutions for one like this. So let's just go through and do a couple of examples. Let's start by doing one where we solve by graphing. So graphing the line is easiest, because all we have to do is go to the y-intercept, which is 6, and then the slope is 2, which means 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and so on, and then connecting those with a straight line. Like this. So that's our linear graph. Graphing the quadratic, I would probably want to, I need to have a technique for graphing it. When it's in standard form like this, I can tell certain things about it. Like I can tell the y-intercept. The y-intercept is always the constant term. So I know that the constant term is going to be 3. But that's hardly enough to graph it. I could also get the zeros easily, though, by factoring it. All right, so this is an easy one to factor. All I need to do is find two things that multiply to give positive 3 and add to give 4. And that would be 1 and 3, right? 1 times 3 gives me 3. 1 plus 3 gives me 4. If they're both positive, then that works out. And from that, I can tell that the zeros are therefore -1 and -3. And so the zeros, there's -3 there, there's -1 there. That means if I probably have enough to graph it at this point. The axis of symmetry is obviously between the -3 and the -1, so it's going to be at -2. Just looking at a step pattern, I think I could guess that the vertex is going to be down here at -2, -1. But I could always just plug the axis value back into the equation as well. So if I put -2 into the equation, -2 squared is positive 4. I'm just mentally filling it into this equation. So positive 4 minus 8 would give me -4, plus what? 3 gives me -1. So I didn't write it out, but mentally just plugging -2 into that equation gives me -1, which is what I had predicted anyway. So here's my quadratic graph based on the points that I have here. I guess I need to be a little bit more careful. I mean, let me backtrack for a second and just explain where I'm coming from. So if I know it looks like this, then I know that my vertex is here. I go over 1, up 1, then I'm going to go over 1, up 3. I know that the step pattern is going to go 1, 3, 5, 7, and so on because it's not vertically stretched. So over from this point at 0, 3, I'd go over 1, and my next step would be to go up 5 from there. So I'd have a point here, and then the next one would be over 1, up 7. That's off the graph. And being a parabola, it's going to be symmetrical, and I'd have another couple points over here. So I was sketching that, but I was just doing it in my head, and I thought I should probably explain that a little better. So there is my sketch for the quadratic. What matters is where they cross. We can see that it crosses here at -3, 0, and it also crosses here at 1, 8. Those are my 2 points of intersection. So there's two solutions. The solutions are getting a little sloppy there. -3, 0, and 1, 8. Okay, so 2 solutions for this one because there's 2 points of intersection. Let's move on and see how we can do it algebraically. So again, substitution is what we want, the approach we want to use. Remember, substitution, we rearrange one of the equations, or both if necessary, so that we've got one of the variables by itself, and then substitute what it's equal to into the other equation. In this case, since we're doing a linear and a quadratic, we probably want to put them both so that y is by itself. So if they're not already written so that y is by itself, we want to do that. If we look at this example here, we can see that y is by itself in both equations. So that first step's done for us. Then we're going to set them equal to each other. Basically what we're doing is we're going to take one of the equations and substitute in the other. So using some terminology that you may be familiar with from grade 10, maybe I'll call this equation 1, and I'll call this equation 2, and I'm going to substitute equation 1 into 2. So what I'm saying I'm doing is I'm going to take, since in this first equation, y is equal to x squared plus 4x plus 3, I'm going to take that x squared plus 4x plus 3 and replace it, or put it into the other equation, replacing the y. So I'm substituting the y value from equation 1 in for y in the other equation to combine them into a single equation. When I do that, I got x squared plus 4x plus 3 equals 2x plus 6. All right, so I've combined them into a single equation by substituting one into the other, and the benefit of doing this is that now I only have one variable, just the x, no longer have the y value to deal with, and one equation with one variable can be now solved however I want to do it. So the way I'm going to solve it is I'm going to put this quadratic, it's a quadratic equation, now I'm going to put it into standard form by moving the 2x plus 6 over to the left-hand side. So x squared plus 4x. I'm going to move the 2x. I'm going to keep the terms in the order I like to have them. In other words, I'm going to have the x squared term first, followed by the x terms, followed by the constant terms. So I'm going to, as I bring the 2x and the 6 over, I'm going to insert them where they would logically go. So after the 4x, I'm going to write the minus 2x I get from bringing that over. Then I'm going to have the plus 3, and then I'm going to have the minus 6. So I'm changing the 2x and the 6 to negative because I'm bringing them to the other side, right? Then I'm going to simplify. So I still just got x squared, but 4x minus 2x equals 2x, and 3 minus 6 equals negative 3. And so now I've got a simplified quadratic, and I can solve it however I can solve it, right? I can factor it, would always be best because it's quickest. If I can't factor it, I could go to the quadratic formula. If we're just doing homework stuff, then yeah, we could use Desmos and see where the x-intercepts are, but one way or another, I need to be solving it. So I'm going to start with factoring, because that's always the fastest if you get good at factoring. And this one looks factorable to me. Two things that are going to multiply to give negative 3 and add to give 2. Well, if I pick 3 and 1 and make the 3 a plus 3 and the x a minus 1, then I know that 3 times negative 1 does give negative 3. 3 plus negative 1 does give positive 2, so that would be my solution there without having to do any more work to it. And then from that, my zeros would be x equals negative 3 and x equals positive 2. Sorry, positive 2, positive 1. Not sure where that came from. So I've got my two x values. Remember, going back to this question here, the solutions were ordered pairs. Basically, I've done the equivalent of finding the x values of my two ordered pairs so far in example 2. I still need to get the y values. So when x equals negative 3, then I can substitute it back into either one of these equations here, the quadratic or the linear, because it's on the graph's it's gonna be on both of these lines, both of these graphs. So I hope it's obvious that working with the linear one is going to be less work. I might as well just plug it into the linear equation to find out what y is. So when x equals negative 3, then y is going to equal 2 times negative 3 plus 6. Again, I'm using this linear equation just to find out what the y value is. And 2 times negative 3 is 0, and, 0. It's negative 6 plus 6, getting ahead of myself. So y is going to equal 0 when x equals negative 3. So one ordered pair is going to be negative 3, 0. And then I'm going to do it again when x equals positive 1. And I'm going to substitute it into that same equation. Might as well go with the linear one again. When x equals 1, y is going to equal 8. And so my solutions are negative 3, 0, and 1, 8. So again, a couple of points. This obviously has two solutions. Solve this linear quadratic system. Okay, in this case, you'll notice that this second equation doesn't have the y isolated. I don't have to have them both isolated, but I like to. It's better. So I'll just call the first one the quadratic one, equation 1. But I'm going to rewrite the second equation. I'm going to bring that 2x to the other side, and I'm going to write it as y equals 2x minus 2. And that'll be my equation 2. And then I can sub 1 into 2 like I did before, which simply means replace the y in equation 2 with x squared minus 2x plus 2. And again, so I've really combined these two equations. And then just go up here where I got a bit more space. If I bring everything to one side to write the quadratic in standard form, I've got x squared minus 2x. Bring that 2x over from the left, and I got another minus 2x. And I've got plus 2. And I'll bring that 2 over from the other side, and I got another plus 2. So I bring all the terms to one side, collect my like terms, simplify. I got x squared minus 4x plus 4. And again, I need to solve this. So again, I start with factoring. Are there two things that I can multiply to get 4 and add to get negative 4? Well, nothing springs to mind immediately. I could try the quadratic formula. Let's see. Let's jump to that and just see what that gets us. So negative b, so negative 4, plus or minus the square root of b squared minus 4 times a times c You know what? As I'm doing it, I'm suddenly realizing that I did overlook an obvious factor. I'm going to play it out. I'm going to tell you what it is now. It occurs to me that again, we can miss things, but this is a perfect square trinomial, which I'm not sure why I missed, but I'm seeing it now. It does have the factors x minus 2 times x minus 2. So I missed that earlier on. I've already started doing the quadratic formula, so I'll carry that out. But you guys probably saw that ahead of me, didn't you? And were wondering why I missed it. Well, we all make mistakes. Anyway, so I got 4 plus or minus, and so then I've got negative 4 squared is 16, and negative 4 times 1 times 4 is also 16. So what this ends up being is 4 plus or minus the square root of 0, which is still just 0. So the plus or minus part is going to end up not mattering. So I'm just going to end up with 4 over 2, which gives me 2. So I've got a single x value. And to backtrack, to fill in what I should have done the first time, is I should have noticed that I could factor this as x minus 2 times x minus 2. My goodness, why is my Apple Pencil being so messy? Sorry, let me try to redo that. Minus 2. And so from that, I would have seen that x equals positive 2 with much less work, which is, again, why factoring is better. But either way, I got the x value of 2. So there's only a single 0. It's going to look like this one up here. Where was it now? It's going to be something like this middle one where it only touches in one place. I just have to find out what the y value is that goes with it. All right, so I can plug that into either equation, but again, I'm going to substitute it into the linear equation. So when x equals 2, y is going to equal 2 times 2 minus 2. So I'm plugging this 2 here into the equation. And y ends up equaling 4 minus 2 is 2. So when x is 2, y is 2. So there's one solution. So the solution is the point 2, 2. So that's an example of just a single solution. Predict the number of intersection points without determining the POI. Well, if I'm going to do that, and I assume I'm not supposed to use Desmos, because I think that would be cheating in this case, what springs to mind when to do this one was, let's put them together into a single quadratic again, and then just see, using a technique we've learned before, to find out how many zeros there are of that combined quadratic. So if I were to combine, if I was going to substitute, say, this equation into this equation, we've seen what to do before, so I'm going to end up getting 3x squared plus 12x plus 14 equals 2x minus 8, right? That's just doing a substitution like I did in the last couple examples, remembering that f at x is just y and g at x is just another y, so they're just, substituting one of the y's for the other one. Combine my like terms. Again, bring everything over to one side. So I got 3x squared plus 12x minus 2x plus 14 plus 8. Again, bringing over the 2x and the minus 8 and changing the sign as I do it. Collecting my like terms. So I got 3x squared plus 10x plus 22 equals 0. So I've got a quadratic in standard form. Remember, the way of finding the number of zeros without actually calculating the zeros when you've got it in standard form is to use the discriminant. and that would be b squared minus 4ac. If b squared minus 4ac is greater than 0, there's going to be 2 solutions, so 2 POIs. If it's equal to 0, there'll be 1 POI, and if it's less than 0, there'll be no solutions. So B, A, B, and C are 3, 10, and 22. So 10 squared minus 4 times 3 times 22 equals 100, minus, I'm not sure what 12 times 22 is off the top of my head, 264, bigger than 100. I probably could have guessed that. So I get negative 164. Again, that negative answer for the discriminant tells me that there's 0 solutions, no solutions. So there you have it. It's extending what you know about linear systems so that now we can do it with linear quadratic. We can have systems of anything. So we could do quadratic. We could do exponential quadratic, although that would get kind of weird as far as solving it goes. We can combine any kinds of functions, though, is my point. And the points of intersection will always be our solutions.